Welcome back, everyone. Assuming you came back and aren't new. If you are, I'm Brent Langston. I'm a senior developer advocate on the containers team. So we wanted, as part of today, since reInvent was so recent, just 2 weeks ago, we wanted to make sure that we covered sort of a recap of stuff that was announced at reInvent. There was a flurry of announcements. I want to make sure that I cover things that are container related. So that's what today is about. That's what this session is about. We're going to go over some container related reInvent announcements. And then I want to demo one of the ones that I'm most excited about. So let's start by talking about App Mesh. App Mesh is a new service that we announced at reInvent, and it's in public preview, which means all of you in this room are able to start using it today. It means none of you in this room should start using it in production. So there's going to be a lot that changes by the time we go GA. We are reserving the right to make breaking changes. So we want to be able to modify APIs and perhaps in ways that will make them incompatible with anything that you've written. So we want to at least warn you by labeling this preview. Don't run production workloads against this or anything. But start looking at it, start using it, and give us feedback. Because it's in preview, we are especially interested in collecting feedback on what your thoughts are, the ways that you imagine you would use this in production, and so forth. But let's start by defining, well, what is App Mesh? I want to ask the question of the room. You might have discovered this. I ask the room a lot of questions. Does anyone today use any kind of mesh service? No one in the room. Amazing. Has anyone asked themselves, as I'm breaking my monolith to microservices, this is a pretty common question, by the way. As I'm breaking my monolith to microservices, really I'm going to start having a whole lot of services that are now going to have to talk over the network. So the network is suddenly going to become even more important than it ever has been. So have you guys thought about that? Okay, cool. Some hands. Good. Good. Smart. So as you start to think about that, the network becoming so important, you'll find that in the beginning anyway, customers were starting to realize that, you know what, I need to have an edict. Every service needs to, for example, needs to have retries. So there needs to be retry logic. And if you've ever written retries, there's a few ways to do it. But there's one important thing that should go along with retries. Anyone know what you do when you write retries into your service? How should they retry? With backoff, thank you. There are some famous outages caused by retry logic that doesn't have backoff. Talk to me, after sometime. I'll tell you a funny story. So retry logic should include backoff. So now all of a sudden you have requirements for your requirements. I require every service to have retry logic. I require all retry logic to have exponential backoff. Okay, well that's great, but I just want to write my code. I just want to focus on writing my business logic, and I don't want to have to think about all the stuff that you need in order to run my service. So customers will then start to say, well, don't worry about it, I'll write it for you, and I'll make it a library. So all you need to do in your code is just include my library. Great. But you don't have a library written in the language that I want to write in. So now all of a sudden customers are having to support multiple languages of libraries that include, among other things, requirements like having retry logic with exponential backoff. So the answer to all of this is, well, what if we can just, in a generic way, come up with a layer for the network that has all that built into it? So instead of it having to exist in the code, we can just have it be part of the network. Instead of having to have service discovery in the code, we can just have that be part of the network. So all I need to do is hear an incoming connection and respond to it, or make an outgoing connection and take in whatever I receive. And that's all I need to worry about in my code, and everything else can be taken care of for me. That's the promise of a mesh. A mesh gives us the ability to extrapolate all of the requirements for talking service to service out onto the fabric of the mesh. And then any language is free to have that communication just run over the mesh and inherit those functions automatically. So there are some meshes out there already that you can run. I won't list them, but there are a few. They tend to be confined or constrained to whatever cluster they're running on. So one of the cool things about App Mesh is it works just like those, except it's not constrained to a single cluster. So if we look at a service mesh just gets deployed right alongside your service. So this would be the code that I may have written as a developer, but instead of me talking to some other random horizontal service over service discovery, I'm just going to talk to a sidecar proxy. And the sidecar proxy is going to see what I'm trying to get at, and it's going to route my traffic to the appropriate location. And it's going to do it with exponential backoffs, or excuse me, with redispatch. So if I reach out to that destination and the destination isn't there, it may have just died, what happens to that transaction? I want it redispatched to another healthy container so that my request can still be serviced. So these are a couple of examples of what I get just by running a service mesh. So Sidecar is deployed alongside all services in a service mesh. But as you can imagine, that means you have to manage the configuration of all of those sidecars now. So, customers historically, when they think about breaking a monolith into microservices, they go from a handful of big services to hundreds or potentially thousands of microservices. And managing those has been daunting, and that's how ECS helps, that's how EKS helps. It helps orchestrate those services. But now we're talking about, virtually doubling the number of items to manage, because now for every one of those instantiations of services, we're going to have a sidecar, and we have to manage the configuration of all of those sidecars. So we have a control plane that can manage that configuration. So data plane is the sidecar, control plane is the management of that sidecar. So the service mesh plane handles figuring out what route should be used, figuring out the monitoring and health of every service, and it'll deal with security. If we want to layer in TLS encryption between all of these nodes, we can do that, and we can manage that configuration and that TLS setup using the control plane. Excuse me. So, App Mesh gives us a control plane that we can use to monitor, manage, and control all of our microservices at scale and manage the sidecars for those services. So in this example, microservice A is trying to talk to microservice B and C. But when it tries to reach out to microservice C, the traffic is just what happens. Let's say microservice C is having a problem, so it tries to make the connection fails. Either it just never connects, in which case I hope you've remembered in your library to write a standard timeout, or the connection is reached but gets back in error. So in either case, that transaction is just gone. We either return an error or we never really return, at least not in a timely manner. We never return any result from microservice C. So microservice A is very likely just going to serve an error back to the customer. So we want to eliminate that. We want to try and improve that situation. So with an app mesh, proxies are running alongside each of these services. So when the connection to microservice C is attempted and fails, then the proxy notices that and says, you know what, I'm going to redispatch that connection to another copy of microservice C, and hopefully that works. So as long as that works, then I can still serve back a result to the customer. Did everyone follow that? Cool. Okay, so why AWS App Mesh? Well, external traffic is going to come in to the proxy, and then the proxy is going to route the traffic to the microservice. So we can more or less deal with both outbound traffic and inbound traffic, and the microservice itself is only ever communicating with the proxy. So this can also help when it comes to security, for example. We know what traffic to expect, and we know that only the proxy is actually going to be communicating in and out. So if anything is ever compromised in the application, we can set it up so the application never communicates out. It can't communicate out. It can only communicate through the proxy. So we get a little bit more isolation by running things this way. The proxy that we're deploying is Envoy. I think this is an open source project, I believe from Lyft. Someone look that up for me. I think it's Lyft though. But this open source project has very quickly become one of the most popular sidecar proxies to use in a mesh. So we knew that customers were already using this. From our observation, it looked like this was the most popular, so we wanted the least shift. So we said, you know what, we're going to build App Mesh, at least to start with, to work with Envoy Proxy. So the proxy layer, the data plane layer of this service is Envoy Proxy. So how do you do it? Well, ELB will route traffic into your virtual node, and your virtual node will have a listener, and then it will have a sort of notion of service discovery to be able to route traffic to other backends that it needs to reach, and then it will have knowledge of other horizontal services that are backend services. So in this example, the virtual router, sees that, hey, traffic is coming into Slash. So I'm going to send that traffic to one of these virtual nodes, and it's going to respond. But we might then have, whoops, I thought I had another slide, where the prefix might be something more specific, like shopping cart or catalog or something like that, and we can route that into a different set of services. And all of this is happening over the mesh. And then as services need to talk horizontally to each other, they can also route using this same virtual router style over the mesh. So all we're paying attention to are the headers that are being asked for through the virtual router. CloudMap is another announcement from reInvent. So I talked in the last session about service discovery. Imagine, and I mentioned that service discovery was Route 53 based, so you do a DNS query. But what if you want to discover something else that isn't a service running in your cluster? Or what if you want to have a discovery mechanism that is API based instead of DNS based? Or you need to look something up according to tag. So CloudMap gives us the ability to have an API that we can call to see virtually everything related to our account's inventory. And we can understand that, for example, if I need to write some data into an S3 bucket, I don't need to hard code the name of the bucket into my application, or I don't need to write it into the environment anymore. I can actually discover it using CloudMap. and I can try and find what is today's version of the bucket, for example. Maybe I shard by day, and every day I have a new bucket that I'm going to write data into. So I can actually do that using CloudMap and do searches by tag, searches by environment, and however else I want to carve things up until I get to a single result that I know is going to be my result, and then I start writing my data into that S3 bucket. So CloudMap is something that's really cool. I hope it solves some problems for you. I have an interesting one for an application that I run. The application needs to know what availability zone it's in so that it can order itself. And it needs to know I'm in the first, second, or third of the 3 availability zones. And that works beautifully in almost every region because we only have 3 availability zones. So when I wrote it, it worked, so I just was happy. I didn't realize when I deployed it to US East 1, US East 1 has 6 availability zones, and I'm not always getting the 6 A, B, starting with A, then B, then C. Sometimes I'm getting B, D, F. And my services don't understand how they should order themselves because of that. So as soon as I get home, now that this is launched, I plan to go and rewrite the service to use CloudMap so that it can look up not only where is that one container running, but also where does it fall in relationship to all of the availability zones that are in use. Is it first, is it second, or is it third? So that's just one example of being able to use CloudMap and having an easy solution to a problem that was incredibly hard to solve 3 weeks ago. So we can dynamically look up any version, any tag, any characteristic of a service or a resource in our AWS account. So this is an example of like a backend app either discovering and using a Lambda or discovering and using a load balancer. So this is from the service discovery service. You can discover instances, and then anything with a namespace myapp.com, service name front end, and then you have query parameters that you can pass in and those query parameters together. And you can see that the service needs to be active and it needs to be version 1.0, and so we'll get back a result that we can then process with our application. Excuse me. So this is my favorite announcement. It's Firecracker. Did anyone see the Firecracker announcement or watch the live stream or anything? Cool, a few hands went up. Firecracker is something that we've been working on internally for a while. And not only did we announce it, but one of the reasons it's my favorite is we also open sourced it. So this was announced and released to the public as open source 2 weeks ago. What is Firecracker? Firecracker is effectively what we use under the covers, behind the scenes, to run Fargate and Lambda. So if you've ever wondered, how do you guys launch code so quickly in Lambda? Or how do you guys spin up a container so quickly in Fargate? Or how do I have a guarantee that my workload in Fargate is going to be secure and not run, not affected by someone else breaking out of their container? So Firecracker is what is offering all of this functionality to us. It gives us a different set of security boundaries than containers and then instances. So we don't have to worry as much about container breakout, for example. If someone buffer overflows their application, what can they do inside their container, inside their sandbox? Can they break out of it? Well, if they do, what are they left with? A Firecracker VM. So Firecracker is a micro VM. In other words, that talk that I gave in the first session about how VMs are big and slow, and that's why containers are so awesome, because they're only what you need and they're super fast to start. Well, that actually changes a little bit when we start talking about micro VMs. Micro VMs are not big and slow. They're actually tiny, micro, and fast. Because they're so tiny, they can start up very, very quickly. And because they can start up very, very quickly, we can, for example, launch a Docker container inside a micro VM, and if anything is ever broken out of, you're just left with the micro VM and whatever's inside of that. And we then have a hard boundary to isolate that container with. So very low overhead, very high density, and we get very fast start times. And it also then includes, because micro VMs are built on KVM, KVM is a virtualization technology that's built into the Linux kernel. Because this is all in effectively managed by the kernel, we can have very fair scheduling across all of our VMs. Does anyone happen to know what's the maximum number of Docker containers you can launch in an instance? I don't know why, and I know why I know this. I know this because at my last job I had to launch a ton of Docker containers for testing, and I found out that the maximum you can launch is 1,024. We're going to launch 4,000 micro VMs on a single instance here in a second, and imagine then if each of those had a Docker container inside of them. So suddenly the limitation of Docker is no longer a limitation. We can actually have more containers running per instance if we really want to. So Firecracker gives us secure containers that we can do things inside of, like run your code, run an operating system, run a container. So Lambda, for example, they're able to launch very quickly your code because they're wrapping it inside a micro VM, and that micro VM can start up in a small number of milliseconds. So as I said, this is available open source through the Apache 2.0 license, and there's a GitHub repo, Firecracker Micro VM, I said GitHub repo, so it's on GitHub. Over time, I think we're going to see integration added. So the one I'm excited about the most is Containerd. Containerd is the Docker engine that I think, the vast majority of people that use containers, they use the Docker engine, Containerd, as their image platform. So being able to Docker run your container is really important. Imagine if while you did that, we were not only starting up your container, but we were starting it up wrapped in a micro VM. And imagine then that there was no real perceivable increase in startup time. Startup time on average, I think what we're going to see, I believe, is going to be 125 milliseconds. And to a human, most humans don't perceive anything below 250-ish milliseconds. So no perceived difference in really 125 milliseconds is pretty fast. So to add that in to get the level of security that you're going to get by being virtualized is really worthwhile. Okay, so enough talk. Let's take a look at a demo. Oh, and by the way, there's my closing slide. So I'm going to close the presentation now, and we'll be ready for the demo. So to virtualize, ideally, you're going to do this on a bare metal instance. And in fact, so that way you have access to the hypervisor. And luckily, AWS provides the ability to provision bare metal instances. I don't know, did anyone know that already? This is not a reInvent announcement, but it's relatively new. It happened a couple of months ago, if I remember correctly. So i3 Metal is a bare metal instance that you provision just like you do any other EC2 instance. So when it comes up, I have access to the full host, bare metal, no virtualization already in place, except I can then take advantage of using KVM. So instead, I have some instructions here that I'm going to ignore. I've already done some of this, and I actually installed Cloud9 onto my bare metal instance. Oh, by the way, is this for the back of the room? Is this big enough? Yeah, okay, let me see. Let me work on making it bigger. How's this? Cool. All right. So Cloud9 installed on a bare metal instance. I'm connecting to it using the UI, using the console. I like to do everything in Cloud9. I think it's pretty awesome. It gives me a really cool text editor IDE environment that I can use. And then also I have terminals that I can launch and run. So at the Firecracker site, the GitHub repo, they actually have a demo. So I've actually cloned it. And then I'm going to cd into it. And in the first terminal, I'm going to run this tiles application. So what this is doing, right now it's not doing anything, but what this will do is show us network activity for all of our VMs. So I haven't launched any VMs, there's nothing to look at, but over as I launch them, what we should see is sort of a snake pattern that builds. So our VMs are built to automatically start up and automatically run iPerf, generate traffic for about 6 seconds, and then sleep for a random amount of time, and then generate traffic for 1 second. So they're going to start with a long trail of traffic. Then you're going to see dots start to happen for those 1 second bursts of traffic. And we're going to do this for 4,000 containers. So I'm curious to see how long does it take to start up 4,000 containers, how quickly does each container start on average, and then the fact that I can start 4,000 and that 4,000 can be generating network traffic all roughly at the same time, I think is going to be pretty interesting to me. So in my second terminal, that's where I'm going to excuse me, do the work. And I've done the setup parts already. So let's just do parallel start. So while that's running over here, you see our snake pattern starting to show up. And I don't know if the resolution change is going to affect refreshing or not, but you get the idea. We're seeing a lot of startup times, a lot of VMs that are starting and doing their burst of traffic. Let's check back over here real quick. We're still starting our 4,000 VMs.
What are the different colors?
I don't know, actually. And they weren't different colors when I ran this in my terminal. So when that happened, I know red is the long burst of like one direction of traffic, but I don't know what it means beyond that. And we're done. We launched 4,000 micro VMs in 51,672 milliseconds. So 78 milliseconds on average per VM. I mean, that's pretty impressive, right? So you can see how, excuse me, how wrapping a Docker container, you shouldn't be too worried about, added startup time, added overhead and stuff like that, but you still get the benefit of being virtualized. And now you're starting to see that, the traffic is, and the traffic bursts for a little bit of time, and then it goes to sleep again. So we're just seeing, random activity now. But it should be not even, but relatively even, and we don't have any real contention or anything like that. What does a micro VM look like? Well, I don't know. Let's see if we can see what we have here. Has anyone ever compiled a Linux kernel? Okay, right, cool. So here is our Linux kernel, and then we have a root file system that we bond together, and that is our micro VM. So in the root file system, I can actually, my favorite, if config. I'm just going to let this run for a second so you guys can see. If you can't see in the back, it's running, scrolling very quickly. Every VM gets its own network interface, a tap interface. So we're able to, network tap to other VMs if we need to, or route outward if we need to. Everything gets its own IP address in the 169.254 namespace. So if we were to actually look at, a particular device, like number 42, for example. Let's see. ID, if I set my ID to 42, and then I look at that device, it has an IP address of 170. Well, to get to this, I would SSH to its host address, which is one less than this, so 169. And I have an SSH key to be able to get into it. That SSH key is in the root file system of the micro VM that I booted. And you see we're just running Alpine Linux. So very, very simple, very small, lightweight Linux, but it's a full Linux. So I could, potentially imagine embedding new code into this Linux and launching it, or using this to launch a Docker container. What else do we have? If I stop this workload, then it will actually stop sending network traffic. In theory, I would probably see, once in a while, I would see a gray box or a hole in this heat map, but I'm not sure. I never actually spot it. This stuff is happening too quickly. What I'd really like to do is instead send it like a ton of traffic and get it to blow up. So also I've plotted, or I can plot the startup time. The script that I use to start things up recorded startup times for each VM. So GNU plot and execute the GNU plot script, and what I end up with is a boottime.png that was just generated, 12:02. And let's just open that up. So here's boottime.png. Let me resize it so that we can see the whole thing. And now I'll zoom in to bits and pieces of it so that you can see what it's telling us. So this was our maximum startup time, 211 milliseconds. Remember, human perception, generally 250 is where we start to perceive that we've waited for something. So even at the maximum, we really won't notice that we've waited for something. Minimum startup time is 123 milliseconds, and the total mean average 144, standard deviation 16. So we get a very, very fair, very even startup time over the course of starting 4,000 micro VMs. So again, super early. This was just released 2 weeks ago, but I think over the next year, you're going to see integrations into orchestrators and into container runtimes so that your container is going to launch wrapped in something like this whenever it's available. And I think, that's something that's going to be really cool and really exciting, because you'll be able to have more per host. You'll be able to have better networking and more fair networking per host, and you'll be able to have a lot more isolation per host or per container. All right, so if you want, you now have another break for lunch, so I get you out early so that you don't have to wait in line for lunch. I'll be up front if you have any questions, and I'm happy to answer questions on any of these topics or others. Just come find me. Thanks.